Like, welcome back everyone for our last presentation of today's seminar. So I would like to invite our last presenter, Sutirtha Chowdhury. He's a master's bioresearch student. So his project is on developing innovative solutions to reduce carbon emissions and for making impactful changes in regional rotational molding machinery industry and water treatment, water tank manufacturing plant. So I welcome Sudhirtha, and yeah, when you are free, please
Yeah,
you can
I will share my
share your
screen now.
screen and yeah, start.
Can you see my screen?
Yes,
Okay.
if you could like put it in slideshow, you could.
Yeah. So welcome everyone. Welcome everyone. Good evening. Thank you for giving me the opportunity to present my research work today. The name of my research is Innovative Solution to Reduce Carbon Emission and Process Improvement of the Polyethylene Water Tank Manufacturing Plant. So in this research work, in my supervisory committee, I have Dr. Jayanta Parachi as my principal supervisor, Dr. Manul Islam and Ahmed Sharafi and Bosphorus as my associate supervisor. And I also have Mr. Sean Boshudinegi as my external supervisor, who is from Bushman Tanks, for whom I'm working. For Bushman Tanks, we are doing this project. So let us start with the background first. What is rotational molding? Rotational moldings is a process which turns polyethylene powder in a simple metal mold into a seamless, impactful resistant hollow part using heat, slow biaxial rotation, and control cooling. There is no external pressure required for this. In this process, we generally use internal air output thermocouples to heat peak internal temperature window. How to control this one? To control this process, we generally use oven set points. We use heat or cooling dual, rotational speed or cooling ratios. Statistical process controls are done on mass charging and cycle times and log receipts per part. To audit this process, we generally use CFD and thermal audits to improve oven or duct uniformity and cut energy. The most common applications are done by this process are water or chemical tanks are being made. Beans are also made by this process. Kayaks, road barriers, fuel tanks, and HVAC housings are also made. So nowadays I'm doing my HDR internship in Bushman Tanks. So I'm fortunate to see their whole process by myself. So here you can see some three pictures. In the first picture, you can see there is a one person who is pouring the polyethylene powder into a storage, and afterward he will put it into the oven. The oven will shut down the window when they will the doors when they will start the process. In while starting the process, they will start their curing process. In the curing process will run up to 45 minutes, and the mold needs to get 150 degrees Celsius to melt the polyethylene powders. After 45 minutes, the after 45 minutes, they start the cooling process, natural cooling process, where you can see in this video. They are generally using biaxial rotation for this process. Afterward, let us discuss why Bushman tanks are using LLDPE. Because LLDPE has the melt index of 2 to 10 gram per 10 minutes to give the low viscosity for even flow, and the tensile strength is 18 to 23 megapascal, and the elongation is 300 to 500% to keep the ductile even flow at low temperatures. And the LLDPE is one of the most inner plastic available because it doesn't comes in contact with any kind of other components while it has been made. And the Bushman's polyresins made Austrian standards 4020 and are molded to Austrian standards or New Zealand standards 4766 tank designs. Polyethylene powder fuses into a single monolithic shells, no welds, bolts, or joints to corrode or leak. Polyethylene is abundant, recyclable, and lighter than metal, so transportation and low material costs stay low. Pigments and antimicrobial or foam nucleus can be premixed into the powder. So now I will show some literature reviews from the past decade research. The rotomolding industry are keeping all their research very secret, and this is very difficult to find any kind of detailed information on their research and what kind of process they are using in this industry nowadays. So, but we have found some findings. So here from the table we can see Gerardo and his team has found some research, and they have found that there is a relevance on time-dependent heat transfer in a duct. And Ozila has published one research paper where he has shown some rotational molding techniques where it includes process and product quality. And there were five more researchers who has done the simulation based research and where they have done some temperature changes in the duct. There were seven more researchers who has done works on the product quality development, and they have shown the challenges in the mold quality process related to the temperature. While doing the research, we have figured out some research problems, which can be also shown as the research gaps, that the hot and cold spot causes wall thickness variation, longer cooking times, and a higher scrap. CFD-driven duct redesigns and burner placements need investigations. LPG gas ovens dominate the plant's carbon footprints, qualifying the baselines and evaluating electrification. Moreover, less technical research on advanced and improvement heat transition systems in rotational moldings are evident. Poor insulation and leaking cells waste energy, thermal imaging and insulation retrofits need systematic evaluations. As I already mentioned, limited access to the technical information and resources hence difficult to find the feasible solutions, and very narrow research work on dynamic burner fan positions that meet the heat supply to real-time thermal loads. The aim and objective of our research is to analyze the existing operational procedures of Bushman tanks in Dalby to pinpoint the potential areas of the heat losses where they are losing the heats. Afterward, simulate the present circumstances using CFD and acquire insights into the existing state. Afterward, develop a novel system and conduct an analysis by 3D modeling, statistical analyzing using finite element methods, and furthermore, the potential execution of an enhanced system. At the end, the proposal will be given to the company where they will see the potential improvements of the methods and modifications to improve the heat efficiency and reduce the carbon emissions by reducing the amount of LP gas consumptions. The methodology what we are using for this industrial project, it has two phases. In the first phase, we got some reports from the Bushman tanks where they have done already some research by some other industry called Shark Engineering, where in 2019, where they have got some map temperatures, heat transfer analysis, and operational logs and incidents report related to the heat transfer analysis. In the phase two, in ESQ, are going to do the heat balance and the losses in the production process. Afterward, possible causes of the heat loss and defects in current systems. Afterward, I have done some modification in the designs for an optimized heating system that is reducing the carbon emission and consumption of the natural gas. And in the final decisions, we are going to provide some suggestions and modifications to satisfy the Bushman tanks. In the methodology, we have already planned to put some thermocouples inside the ovens. We have planned to put K-type thermocouples inside the ovens to take the real-time temperature log readings. Here you can see the full graphical designs of the ovens. Here they have outlets in the back walls. They have a 6 meter long duct where they have 9 outlets. They have a recirculation fan, and I want you all to focus on the chimney because we are going to discuss about the chimney size, the duct outlet numbers, and the back walls. Now, thermocouple installation process. Here is this graphical image. You can see from the inlet, the air is going inside, and from the 9 outlet is coming. And in the thermocouples, I have already put it inside the duct in some distinct places. And after putting them, we have got some graphical data where it shows the main outlets is getting almost on an average 650 degrees Celsius temperature, and at the end outlets is getting almost 200 degrees Celsius. Afterward, we have planned to change the geometry of the chimney size. Here you can see where my cursor is. This is the chimney and these are the outlets. They have the 4 outlets in the back first. So when we have put for the temperature inside and with the current existing model where they have the chimney size of 200 by 200 mm, we can see here the temperature is not distributing all over the areas, though it gives 225 degrees Celsius in some points, and the ducts are getting almost 373 degrees Celsius, but is not good enough to put forth and give the all over the process 250 degrees Celsius all over the oven. Afterward, what we have decided to make the chimney size 300 by 300 mm. Afterward, it started giving some good results and is distributing throughout the world. But it was not enough to distribute the temperature to the mold. Afterward, we have made the chimney size as the same size of the duct outlets. The duct outlet size was 380 by 380 mm. We have made the same, the chimney size. And afterward, we can see some good results there, like it is getting 328 degrees Celsius in some areas of the walls. But when we have put it in the 400 by 400 mm, it only shows the duct back walls are getting the results. So we have decided to not consider the 400 by 400 mm. Afterward, if we give focus on the temperature profiles, it shows that though it has a good temperature profiles, but the pressure lies in the negative pressure. Negative pressure is never considered good for a duct model or for a oven structure, because if there is a negative pressure there, it will get vibration, there will be more turbulence, and there will be no saturated temperature throughout the oven. Afterward, when we have made the chimney size 300 mm, when we have put the simulation, we are seeing the pressure profile is going to positive, but it was not enough because you can see from the temperature pressure counter line, it still lies in negative pressure. Afterward, in 380 mm chimney size, it lies into the positive pressure, which definitely tells us that now is the decision to make. Now we can set the set point. Now we will make the chimney size 380 mm. But afterward, when we have put it in the 400 mm, it shows that is not good enough. It already putting it into the negative pressure because the chimney size is more. Now, how does the chimney size impacts the ducts inside? Here we can see from the designs in the dividers, they have the more temperature, but inside the duct outlets, it doesn't have the more temperatures. So afterward, in the 300 mm, we can see though it have 270 degrees Celsius inside the dividers throughout the ovens, but it cannot be considered good enough for a good capacity. Afterward, in 380 mm, it gives more saturated temperature and more good temperature profiles, which says us that it will create 350 degrees Celsius on an average. Afterward, now we have given our focus on the duct outlets numbers. Here in the picture, you can see, though it gives 650-degree in from the beginning, but the main problem lies in the velocity. Here in the streamline profile of the temperature, you can see there it has some low temperature profiles in some areas. But in the velocity, you can see it barely shows some yellow lines, which tells us that, which is 3.5 to 400 meter per second velocity profiles, and is barely going to the seventh, eighth, and ninth outlets. Here in this picture, it will make you clear all the things. Like here, you can see, though the seventh outlet is getting the velocity, but is decreasing time by time. And the seventh and eighth and ninth outlet are barely getting any kind of velocity, which in represent that the modification is needed in the duct shape for better outputs in the velocity. Now, here is a difference between how we have changes the duct numbers. If we change the duct, if we decrease the duct number up to 8, what will it give? Now here we can see the seventh outlet will get some velocity as we have decreases the chamber size. Here is the gap between the outlets is 150 mm. Here we have neglected the ninth outlet, but still the the duct area was 6 meter. Here, if we put the difference with the six outlets, here you can see now the velocity is passing through the fifth outlet and going through the sixth outlet. But it gives us that the geometry is not good enough now. So now the geometrical change is needed in the duct shape. Now how the duct shapes make some changes. Now this will give a big change in the geometrical change. Here we have made a L-shaped duct with the 8 outlets. Here we can see the duct outlets are giving almost on an average 300 degrees Celsius all over the duct. Here, Young and her team utilized the fluent porous media model for simulation by defining boundary condition at 4 specific locations. It was our focus to use his techniques. The advantages will be to mitigate the occurrence of the underheated porous zones, which can lead to warping and uneven curing in rotational molding ovens of the powder coating lines. In the graph from the L-shaped duct here, you can see from the beginning, it will give 400 degrees Celsius, and time by time, it will decrease to 202 or 226 degrees Celsius, which is good enough to get the mold enough temperatures rapidly. The gradual temperature decrease at the outlets of the duct, which will help distributing adequate amount of heat to the melt powders quickly by reducing the cycle time. Moreover, no extra insulation will be needed in the structure. Now we have focused on the duct shape. Now we have changed the duct shape. Before that, you have seen it has some shapes. Now we have changed the duct shape to the rounded one. Before that, there was some chamfers on the outlet sides. Now we have reduced the chamfers, and we have made it rounded shape in the outlet zone, and we have made it 6 outlets, and in the below they have the chamfer there. If I think you guys remember that before that the velocity was 3.824 meter per second. But now if you can see the picture now with the 6 outlets with this geometrical shape, it's hitting almost 12.4 to 16.4 meter per second. So on an average, it will give 12.4 meter per second velocity, which is very good for the structure. And afterward, if you can see in this picture, in the third picture, you can see there is very less turbulence over there. And it gives more stimulated pressure all over the streamline pressure all over the area. If there is a low viscosity, there is a good viscosity all over the area, less turbulence there. Now, if we see this graph, here you can see this, where is my cursor is, the nine outlets, standard outlets, it lies down there. And as we have given some five models there, it gives more promising results. The designs with the six outlets, the trimmed one, in the design, in the first design, you can see they have this 7 meter, 6 meter duct, but we in the new designs, we have trimmed it by 750 mm. And here you can see there is a less turbulence there, and it is giving all over on an average 253 degrees Celsius, which gives the most promising results. So thank you. And here comes to the end.